If you're anything at all like me, you probably still enjoy typing in game listings and running them on your BBC Micro, whether physically or via emulation. I've got quite a library of books that contain all kinds of type-in listings, as well as magazines, and while it is true that I could just go and download almost all of them from the BBC Micro Complete Games Archive website and spare myself the time, I still prefer typing them in myself and getting a feel for how the program actually works. But have you ever run into a problem where, despite painstakingly typing in the listing perfectly, character for character, it still refuses to run? What's the deal here? Were these books really just a massive joke at our expense? Were they filled with page upon page of program that was never designed to run in the first place? Granted, it was true that certain magazines did have to print corrections in later issues after typographical errors caused programs to come with bugs. But that doesn't explain it for the books. Surely they would have never made it into print if the programs within their pages never actually ran. Well, what you might be coming up against here is in fact a memory issue. Not human memory, I'm not talking about misremembered ideas about these programs back in the day, but rather the memory of the BBC Micro itself. And that's what we're going to take a look at in more detail now. As we all know, a typical BBC Micro Model B comes with 32 kilobytes of memory. It's right there on the screen when you turn it on. But of that 32K, a sizable chunk gets reserved for screen memory, which is to say the memory required for displaying text and graphics on screen. Now, depending on which mode you're running in, you will have a greater or lesser amount of memory left within which to write your basic program. A fair few type-in listings make use of Mode 2, principally because it offers the full 16 colours. Well, strictly speaking 8 distinct colours and 8 flashing colours, but more on that another time. However, Mode 2 does come at the cost of more than half of the total memory, roughly 20 kilobytes, which leaves just 12K for the program. Except, well, that's not entirely true. The Micro also reserves a further chunk of memory for the operating system and other peripherals, which could include things like the tape cassette drive, the disk filing system, or DFS, or indeed the EcoNet interface. Each of these take up differing amounts of memory. For example, if you have a tape cassette drive connected, the operating system will reserve the first 3.6 kilobytes of memory. By contrast, if you have a disk drive connected, the operating system reserves a whopping 6.4K of memory. This means that if your Beeb is configured to use a disk drive, and you're in Mode 2, you've got just 5.6 kilobytes of memory within which to squeeze your basic program. A lot of the type-in listing books and magazine articles, especially those dating from the first half of the 1980s, were written on the assumption that your typical Beeb user would just have a tape drive, and thus the programs themselves might very well go beyond that 5.6K of memory limit. One such example that I've been playing around with recently is 3D Terrachase, which appeared in the Games for Your BBC Micro Compendium book, edited by Tim Hartnell for Virgin Books. It runs under Mode 2, and if you attempt to type in this program using a Beeb with DFS or an emulator like Beebem, which by default will assume the existence of a virtual floppy disk drive, it simply won't run. Indeed, if you try typing it in using a basic editor, such as the ROM-based Acornsoft basic editor, you may actually run out of memory before you can complete typing it in at all, especially if you try typing the program in under the mode in which it is designed to run. Not, of course, that anyone would ever willingly do that in Mode 2 because it's horribly chunky, but it can still be helpful to temporarily switch into that mode in order to see how much memory is remaining using the tools available to you in the Acornsoft basic editor itself. We can simulate how the original program's author would have expected things to work if we temporarily disable our floppy drive in Beebem. Without a floppy drive, we can't of course load the program from disk, but in true Blue Peter fashion we can paste it in from the clipboard and run it directly. What we're doing here is actually simulating somebody sitting down at their BBC Micro without any kind of disk drive attached and typing in a program listing in a single sitting without at any point choosing to save it to disk. Now, Pasting it in from the clipboard works for us if we're using an emulator, but it's a rather inelegant solution, and in any case it wouldn't be available to us if we were using a physical Beeb with either a Gotek or an actual floppy drive attached. And notwithstanding my earlier enthusiasm for type-in listings, I wouldn't in practice want to sit down and type in the same program every time I wanted to actually play the game. Loading things from memory is all well and good, but after a while you just get a little bit tired. So what should we do? Well, there is a workaround. You can just cheat. Essentially, you write the program, you save it to disk, as many times as you choose to during the process of typing it in, and then when you're ready, you load it from disk, and then you tell the Beeb that actually you don't have a disk drive after all. These are not the droids you're looking for. This technically frees up almost 3K of extra memory, which makes it possible to run the program. Which sounds easy, right? But how do you actually do that in practice? Well, first things first, we're going to need to understand how the BBC Micro's operating system manages memory for basic programs. Now don't panic, we're going to take this nice and slow, and hopefully this will be a refresher for some of you that perhaps knew this back in the day but have since forgotten, and if you're totally new to the way in which memory is managed on a Beeb, perhaps this will be a helpful insight. So we're going to start with the 4 pseudo variables because these really do give us an insight into how the memory is allocated and managed in practice. And those pseudo variables are called page, top, LOMEM and HIMEM. Now these 4 pseudo variables represent memory addresses. If you're confused by the idea of a memory address, try to think about it as really nothing more than a pointer to a particular bit of memory. More accurately, I should say a particular byte of memory, of course, because the memory within a BBC Micro is what is referred to as byte addressable. It means that with a single memory address, I can point to a very specific byte in memory. So if we go back to the 32K, when we say that the BBC Micro has 32K of memory, what we mean is that it has 32,000 bytes of memory, and each of those 32,000 bytes has its own memory address, and you can actually provide a memory address to point at a specific byte within memory. So that's what a memory address is. It's a way of representing where in memory a particular byte might be. Why do these matter in practice for us? Well, when you write a program, it is very important to be able to give the BBC Micro 2 crucial pieces of information. 1, where in memory does the program start? And 2, where in memory does the program finish? Now those 2 bits of information are memory addresses. We are telling the BBC Micro where to find the very first byte of our program, and then where to find the very last byte of our program. And whatever occupies the memory in between those 2 addresses is treated as the executable program itself. Now you might be wondering, how does this differ from line numbers? After all, whenever I type in a program on the BBC Micro, I have to provide a line number for every line of code. Surely the computer is intelligent enough to know that if my program starts on line 10 and finishes on line 100, that's all there is to it. Why should I care about memory addresses? Well, you'd actually be right to think that. Indeed, that's the beauty of the operating system on the BBC Micro. It takes away the bother of memory management from you. All you need to do is start typing out your program and use the line numbers as makes sense to you to allow things like go-tos and go-subs and so on, and the BBC Micro will happily manage the memory addresses all by itself. But for what's going to follow in this video, it is important to understand that even line numbers themselves have a memory address. That's because a line number is, like everything else, a piece of information, and that piece of information has to be held in memory. So actually, the first line of your program, whether that starts with line 1, line 10 or line 1000, that line number is held in memory. Just as the final line number of your program is also held in memory, and it has its own unique memory address. Indeed, it goes one level lower. It isn't simply the line number that has a memory address, but everything that comes after the line number, as in the constituent parts of the code that make up that line. So, in a simple example, line 10 print hello, well, yes, 10 has its own memory address, but so too does the print command, and each of the characters within my print command of HELLO, and indeed the opening and closing quotation marks. Each one of these is an individual byte, and by virtue of being a byte held in memory, each of those bytes have their own memory address. Now, memory addresses are sequential, which means that if I know the starting memory address, then everything that follows after it will be read sequentially in memory. And this is important after all, because if we go back to that simple example, when we say line 10 print hello, that's what we want the computer to do. We don't want it to do line 10 H open quote ELLO close quote print. Quite apart from anything else, this doesn't actually do anything and would just give us an error. But in practice, the fact that memory addresses are sequential means that if we provide the starting memory address for line 10, the computer knows that everything that comes after it in memory will be laid out sequentially and can be executed sequentially. And this is very important for what will follow in the rest of this video. So after that little segue into memory addresses, let's get back to those 4 pseudo-variables that we were talking about, and in particular page. So page tells us where the bottom of our program is, memory-wise. Essentially what that means in practice is that the micro will reserve all of the memory from 0 up to whatever value page is set at. Now the default value for page when a tape cassette drive is connected to the micro is 3584. So that means that from the very first byte at address 0 all the way up to the 3584th byte is reserved. We can round this up and just say that the first 3.6k of memory is reserved if that's easier to work with. Now by contrast, if you have a disk drive attached to your micro instead of a tape drive, the default value for page is 6400. So that means that the very first byte in memory at address 0 all the way up to the 6400th byte is reserved. And we can abbreviate this to just say that the first 6.4k of memory is reserved. Page comes with a companion pseudo-variable called top, and top tells us where the top of our program is. So just as page tells us where the bottom is, top tells us where the top is. And that is to say, it is the memory address at which the next available free byte is located. And although we call it top, it doesn't actually mean the start of the program as you might intuitively think. Quite the opposite, it actually means the end of the program. So if your program has 30 lines of code, for example, top will represent the memory address 1 byte after the final byte of line 30, which is to say the next available free byte. So what this means is that if you subtract the value of page from the value of top, you can see how much memory your program has consumed. By default, top always starts at a value 2 bytes higher than whatever page is when you first turn on the Beeb. So until you start to write a program, those first 2 bytes that start from the memory address of page are, in hexadecimal, FF0D, which, don't worry too much about it, this is understood by the Beeb to simply mean end of program. So it's 2 bytes held in memory that mean you haven't written a program yet. Now if you start to write some lines of code, the value of top will dynamically increase, and indeed that 2 bytes of FF0D will get overwritten with whatever you start to write for your program. Now the third of our pseudo-variables is called LOMEM, and when you first turn on your BBC Micro it will have exactly the same value as top, and if you start writing a program, as top increases, so too does LOMEM. So at any given point in time, LOMEM and top will just be the same value. Which probably makes you wonder, why have we got this third pseudo-variable if it's really just duplicating whatever the value of top is? Well, it serves a different purpose. Top is where is the next available free byte post-program in memory, but LOMEM is a pointer to where the values of variables in memory should reside. And this is an important distinction to bear in mind. When you write a program, you can declare variables until they're going out of fashion. But the variable values don't actually exist in the program code. Even when you hard code the value, it doesn't actually exist in the program code. When you hard code a variable, you're just telling it, this is the value I want this variable to have. but the variable itself is simply a pointer to a bit of memory, and that bit of memory has to exist outside of the program, because the program occupies a sequential area of memory, and variable values change, particularly when they're held inside loops and so on. So it's important for the program essentially to be able to reach outside of itself and reference bits of memory that are not themselves part of the program. So that's why you have LOMEM as a separate pseudo variable, because if you really want to, you can actually set it to be a different value from top. You can do this manually, but it is important to do it only at the start of a program, because of course if you try to set the value of LOMEM to something different partway through the program code, the basic interpreter will get hopelessly lost and all of your variable references are going to break and your program just won't run. So if you're using variables and you want the values of those variables to occupy an area of memory some way past the value of top, because you might be reserving another chunk of memory outside of the program for something else, if you're one of these advanced programmers, then you can set LOMEM to some other value. But as I say, make sure you do it before you start writing the program itself, because otherwise the program is going to get busted. And now we come to our fourth and final pseudo variable, HIMEM. This is an important pseudo variable because it indicates the memory ceiling for our program. Any memory beyond the memory address of HIMEM is reserved for screen memory. This means that if you subtract the value of top from the value of HIMEM, you can see how much memory you've got left for your program. Although it remains a static value within a given mode, HIMEM will change depending on which mode you're in. So for example, in mode 2, the value of HIMEM is 12,288, which represents the initial 12K that we referenced earlier, with the remaining 20K being reserved for mode 2 16-color screen graphics and text. In mode 4, by contrast, the value of HIMEM is 22,528, roughly 22.5K, which means that just under 10K is reserved for screen memory. In mode 7, the most economical of all the Beeb modes, HIMEM has a value of 31,744 because we only need 1K to be reserved for the screen memory. Now, like LOMEM, it is actually possible to manually change the value of HIMEM within a program. Cunning programmers will use this technique to hide extra code within the screen memory. Have you ever noticed weird, scrambled-looking pixels at the top or bottom of a program at runtime? That's actually genuine program code hiding inside the screen memory. It's also one of the reasons why on the Acorn Electron, for example, the screen size of certain games is smaller than it is on the Beeb. A portion of screen memory is being borrowed to squeeze in the additional program code that won't fit into the conventional program memory area. In fact, if we switch into mode 2 for my example type-in listing 3D TerraChase before we load it from disk, you can see this in practice. That scrambled up flashing block of coloured pixels is the portion of the program that has spilled over from beyond the HIMEM watermark of 12,288. This is not, by the way, an example of cunning programming technique, however. Although the program has leaked into the screen memory, this was not intentional, and in any case, I cannot actually run the program in practice. Well, we've gone on quite the journey here, but armed with our understanding of how the BBC Micro allocates memory and the 4 pseudo variables that we can use to manage this ourselves, we should be able to make a reasonable start on fixing our memory overspill in the case of not only 3D TerraChase, but many other type-in listings as well. Now, from what we've covered so far, it might seem tempting to just stick an extra line at the start of the program that sets page to a lower value, and hey presto, we've solved our problem. But unfortunately, that's not going to work. Why is that? Well, if you think about it, when you first turn on your Beeb, it will set the page to its default. Now, if you happen to have a disk drive connected, that default is going to be 6,400. Now you load your program from disk. So the Beeb will copy the program from disk, and the first byte of that program is going to be at memory address 6,400. Okay, so far so good, but what happens if the first line of our program then sets page to a different value? Well, we've got a problem here, because what we're now saying is that the start of our program is some other memory address, and that's not where our program is. We haven't loaded the program into that lower memory address. It's still sitting in address 6,400 and bytes forward from there. So if the first line of the program redirects the computer to look for more program at a lower memory address, it's going to get hopelessly confused. because there probably isn't anything in that memory address at all. So it's going to scan through a series of empty bytes and not have anything to do, and then the first available byte that it reaches after that is going to conflict with the first line of our program. In fact, it can get worse than that, because sometimes it may well come across some bytes in those earlier memory addresses and it won't know what to do with them, because they won't look like lines of basic code, they'll look like something else. Either way, the likelihood is that you're going to get a bad program error, syntax error, or possibly both. So unfortunately, this apparent trick of just tweaking the page value within the program, even if you do it at the start of the program, is not going to free up the additional memory that we need. Instead, what we need to do, other than resetting the page value, is to copy our program byte by byte to a new location in memory, starting from the position that we want page to be. Only after we've copied the program can we then safely reset the value of page to match it. What this does is it allows the Beeb to start executing the program correctly from the new page value. If we make that starting memory location lower than the default, we are able to reclaim some of the previously reserved memory. Obviously, we do have to be careful not to copy our program too far down in memory, because that would potentially see us overwriting some important memory areas that are legitimately reserved by the operating system. However, if we use the default tape cassette page value instead of the disk one, then all we're doing is eating into some additional memory that was previously reserved specifically for the disk drive. And if you think about it, once we've loaded our program from disk, we don't need to reserve that memory anymore. Copying an existing program from one memory location to another is actually a lot easier than it sounds. We can do it with a simple for loop. We define the loop to start from 0 and go up to the total size in bytes of our program. And we already know that we can calculate that by subtracting the value of page from the value of top. We then iterate through the loop in steps of 4, because it's possible to copy 4 bytes at a time using the shriek or exclamation operator. And inside the loop we specify that our new starting position, that would be the page default for the tape cassette drive, and we add our iterative loop variable to that starting position on each go round of the loop. By the time the loop concludes, it will have copied each byte of our program in sequence, starting from the new position in memory. Next, we have a bit of housekeeping to do. First of all, we're going to need to adjust our top value in order to tell the BBC Micro where our program finishes. Why do we need to do that? Well, all we've done so far is copy our program to start from an earlier memory address, but we haven't actually moved the program that was originally loaded into memory. In fact, that original version of the program is still there in memory, or at least part of it is. Some of it will have been overwritten in the process of copying our program to start from an earlier position in memory, but the end of the program that was originally loaded into memory is still there in those same memory addresses. And we need to make the Beeb aware of where our copy of the program ends, otherwise it's going to try and carry on executing old chunks of the original instance of the program that are still sitting there in those later memory addresses. Bear in mind also that the original value of top is quite a lot higher than the end of our program now is, and in the case of 3D Terror Chase, that value has eaten into the screen memory, so that's another reason why we need to amend it. But top behaves rather differently from page, LOMEM and HIMEM. You can't directly change it. You can try, but if you do, you'll just get a syntax error. So is this where our story ends? Are we in fact unable after all to cheat and move the program to a lower memory address because we can't now tell the BBC Micro where that program finishes? Of course not. We might not be able to manipulate top directly as a pseudo variable, but what we can do is change the underlying value that top is pointing at. But what do I mean when I say that? Well, as I've been careful to say up to this point, top along with page, LOMEM and HIMEM is a pseudo variable. That means it's not a real variable in the true sense. It's more like a label. In the case of page, LOMEM and HIMEM, you can both look up what that label is pointing at and indeed change the value that it's pointing at. But that's because in all three of those cases, page, LOMEM and HIMEM are fairly static values for the duration of the program, and you could choose to adjust them to a different static value, but it's still a static value that is not affected by continuing to add new lines of code to the program. Top is different. Every time you add more content to your program, top is changed. Now, you as the programmer typically don't want to have to be bothered with keeping the BBC Micro up to date with where the next freely available byte is in your program. That's what you let the operating system do, and therefore the consequence is that the operating system will not let you directly change the value of top because it says, hey, that's mine, leave it alone. But if you know where in memory the top value is actually being stored, you can just bypass the top label altogether and just go and poke a new value into memory at that location. This has the effect of adjusting the top value. So if you were to then query top, you would see a different value. But what do I mean by that? Well, without getting too esoteric about it, memory addresses are pieces of information just like anything else. That means that they can be stored in memory too. I can store a piece of information in memory that is itself a memory address. So now my memory address I'm storing has itself a memory address that points to a memory address. It's something in programming that's referred to as indirect referencing. If it seems a little bit mysterious, try and think of it like this. Imagine I've got two friends, Bob and Susan. Bob isn't here right now, Susan is. I want to know where Bob is, so I say, hey, Susan, where's Bob? Susan says, oh, Bob, he's down the pub. Now I know where Bob is. He's not here, but by asking Susan, who does know, I'm able to find out. It's kind of similar with memory addresses when you use indirect referencing. You might not know where the next freely available byte is after the end of your program, but by saying, hey, BBC Micro, tell me the value of top, it returns a value. 6402, which is the memory address of the next freely available byte, so now I know where it is. But that value, 6402, must itself be sitting somewhere in memory so that when I say, hey BBC Micro, tell me the value of top, it's able to retrieve it and print it on the screen. So in principle, if we know the memory address that is storing the memory address that is returned by top, we could change it to something else, a different memory address. It would be a bit like Bob saying to Susan before he goes down the pub, hey, if anyone asks, tell them I'm visiting my mum. Then if I had asked, hey Susan, where's Bob? Susan would say, oh, he's visiting his mum. That's effectively what we're doing here. We are cheating the system because as far as the BBC Micro's operating system is concerned, the value of top is the next freely available byte after the end of the program from when it was loaded from disk. Now what we're doing is manipulating that so that instead, when we say what's the value of top, it looks to its memory location where it's expecting to find the value of top and returns a different value, namely the value that we're about to put into that memory location ourselves. Of course, if we're going to put a different memory address into the memory address that stores the value of top, we need to understand how memory addresses work and also what that memory address actually is. Now, the BBC Micro manages memory across what are called memory pages. So the first memory page indexes from 0 and is therefore referred to as the 0 page of memory, and each subsequent page of memory iterates by 1. So you have the 0 page, then page 1, page 2, etc., etc. Each one of these pages of memory has 256 locations on it. So the 0th position on the 0 page of memory would be the very, very first memory address in the memory map of the BBC Micro. Now the 0 page is quite special because you can actually reference a location on the 0 page of memory without telling the BBC Micro the numbered page that you're interested in. It will default to 0. So that means that I can actually reference memory addresses on the 0 page of memory with just 1 byte. All subsequent pages of memory from page 1 forwards, I need to provide 2 bytes for my memory address. The first byte designating the page and the second byte designating the location on that page. Now, as luck would have it, when it comes to the top value, this is actually stored on the 0 page. But this is where it gets a little bit tricky, of course. Although the value of top is stored on the 0 page, it's storing a memory address that could be anywhere in memory. So it needs 2 bytes of memory to be able to store the memory address that represents the next freely available byte at the end of our program. With me so far? That means that we need to know where on the 0 page the first and second bytes are in order to be able to manipulate them to some other value if we want to change the value of top. If by happy circumstance you have a copy of the Basic ROM User Guide to hand, which I do, you will find a very useful section in that book which explains which bits of the 0 page are reserved by the Basic ROM and the operating system for various purposes, and indeed, as it happens, it tells you where the value of top is stored. It is stored at the 18th and 19th bytes of the 0 page, the 19th byte telling you the page number and the 18th byte telling you the location on the page. So now we know where the value of top is held in memory. Strictly speaking, if we want to manipulate the value of top, we should have to manipulate both the high and low byte, i.e. the page number and the location on the page. But as it happens, if we move the value of page from a default of 6400 to the new value of 3584, which is to say, change the default for a disk drive being connected to the Beeb to the default for a tape drive being connected to the Beeb, we actually move the memory address of page by a multiple of 256. If you don't believe me, let's do the sums. Let's imagine that our page value is 6400. We now move it back to 3584, which is a difference of 2816, which if we divide it by 256 gives us a value of 11. What that actually means is we have moved the value of page 11 pages back. That's essentially what it translates to. So what that means is that the location on the page remains the same. Because we've moved it by a multiple of 256, all we actually need to do is adjust the memory page for the value of top, because the location on that page will still be the same. Remember, all that we're doing here is copying our program to a new starting location in memory. The program itself is exactly the same, and it is exactly the same length in number of bytes. Through the magic of 8-bit, because the program we have copied is the same size as it was before, then provided we copy our program to a new starting memory address that's a multiple of 256, the new value of top will still have the same lower byte value as before. Only the higher byte value, which is to say the memory page number, will have changed. To illustrate this, let's keep things simple for a moment. Imagine our program is just 10 bytes long and we have a page value of 990 with a top value of 1000. Remember, top is the next available free byte, so our program occupies memory locations 990 through to 999, and the top value of 1000 is the next freely available byte. Well, if we express this as a 2-byte address, it will have a high byte of 3 and a low byte of 232. That's because we always multiply the page number by 256, which in this case 3 multiplied by 256 is 768, and then we add on the location on that page, which is 232, to get a value of 1000, which is our memory address of top. Now let's imagine that we copy our program in memory with a new starting address that's 256 bytes prior. So that means that our new page value is 734, because obviously 990 minus 256 is 734, and our new top value is 744. The program occupies memory addresses 734 through to 743 inclusive, and 744 points to the next freely available byte. Well, all we need to do is adjust the high byte to be 1 less than before. We've moved it 1 page back. So 2 multiplied by 256 is 512, and if we add our existing unchanged low byte value of 232, we get the desired 744. Might sound a little bit complicated when we spell it out in the maths, but really it's very simple. Provided you move programs in multiples of 256, all that you're really doing is moving the program to a new page in memory, but the location on the page, both for the starting and ending position of the program, will remain the same. We can directly adjust the value of a byte in memory by using the query or question mark operator. In this case, we want to set the value held at memory location 19 on the 0 page to a new high byte value. The high byte is the difference between our original page value and the new page value we have defined, divided by 256. By using the div operator, we keep this as a whole number and disregard any fractional amounts. These are already captured by the low byte, which, as we've demonstrated, we don't need to adjust anyway. All that remains is to now officially set page to its new value, which we can safely do because we've now copied the program to start from that new memory address, and then adjust LOMEM to keep it in sync with our new top value. If we didn't do that, then despite copying the program, the Beeb would get into a muddle for any of the variables that are contained within the program. And that's pretty much all there is to it. It might have felt like we've been on a bit of a journey here, but what we've ended up with is a few lines of code. We could load our program from disk and just run those lines in a single one-line statement using colon delimiters and then subsequently run our program, and that would work just fine. In fact, we could do it just to prove that this does work. But it has to be said, it is a bit of a pain to have to remember to do it every time we load the program from disk. Better still would be to incorporate these statements into the program directly, so that whenever we load it from disk and run it, the copy routine and the pseudo variable tweaking is just done automatically. In fact, if we wrap it inside a proc, we can use that same routine in other programs as well. Of course, incorporating the memory copy routine into our program has to be done with care. If we simply make a call to our memory copy routine at the start of the program, we will end up putting it into an infinite loop, because it will copy the program to a new location and then attempt to run it, but the very first line of the program will tell it to copy the program to a new location, and so on and so on. It will run, copying our program to a new location in memory without ever actually executing the code after the copy routine. To prevent this, we have to put in a simple if statement to check whether or not the page value is greater than the memory address that we actually want our program to start from. On the first execution, page will be 6400, the default for a disk drive, and so the program will run the memory copy routine and attempt to then run the program again, having copied it. However, at this point the value of page will now be 3584, and so the memory copy routine will not be called, and instead the remaining code of the program, which is of course to say the program itself, will be run instead. And in this way we avoid an infinite loop of copy routines. It's quite a good idea to pop an asterisk fx200,3 at the start, because the memory copy routine does take 1 or 2 seconds to run, and we really don't want a user hitting escape midway through. Otherwise we'll end up in a right pickle with half the program copied elsewhere, but the page and top values still set to their original values. Chaos ensues. And that's it. All that remains is to fire up the game and enjoy the fun. I mean, we hope it's going to be fun after all that effort of typing it in and bolting on a memory copy routine, but let's face it, it could turn out to be a dud. That's the lottery of type-in listings. Like Forrest Gump and his box of chocolates, you never quite know what you're going to get. But if it does turn out to be a dud, you can always adapt it, using similar techniques that I've outlined in this tutorial, and maybe some others in future videos as well. In the meantime, I hope that you found this informative and that it has answered the question, why doesn't my BBC Basic program fit into memory, and perhaps also revealed that those type-in listing books and magazine articles weren't lying to us after all. That's it for this video. I hope you'll join me for the next one in the series, and until then, goodbye!